Well, thank you so much, first for asking me to visit Szeged again after several decades since my last visit here, and for this very detailed and most accurate introduction. Now, my title is with NMR of biological macromolecules to a Nobel Prize. Now, NMR stands for nuclear magnetic resonance. It could also be no more research or no meaningful results, but it is nuclear magnetic resonance. And biological macromolecules are either proteins or nucleic acids. Now, I'm not going to give a technical talk today. I will try to let you see how a career in science can take strange turns. And I think the most important introductory statement is that when you get an opportunity, then go for it. It may not come back a second time. I recently found this quotation, which has been mentioned in a 2018 article in the Royal Society Journal of the History of Science. It says, research needs a bold and invigorating frame of mind, which may be uncomfortable to others. That means if you feel that you have a mission, then go for it, even if it may make you unattractive for some around you for a while, usually. Now, my obstination was in this technique. It's now spelled out, nuclear magnetic resonance. Nuclear magnetic resonance is a physics principle. The Nobel Prize in Physics was awarded in 1952 to two scientists who worked in the United States, one of which came from my university, the ETH in Zurich. Bloch and Purcell are their names. Now today, the physics principle of nuclear magnetic resonance can be used in two very different areas. On the one hand, for studies of molecules, where we deal with dimensions of 10 to the minus 9 meters, or thereabouts, 1 angstrom, or we can study macroscopic objects, in particular human bodies, using the same principle. And I will refer to both of these possibilities during my talk. First, let us talk about molecules, because this is a field where I was active for most of the time, and which was also the area that was acknowledged with the Nobel Prize. We worked with proteins, and when you look at the chemical structure of proteins, you have a linear array of amino acids. There are 20 different amino acids. And the length of the chains varies between about 30 amino acids to several thousand amino acids. And most proteins that we deal with have 100 to several hundred amino acids. This chemical structure could in no way lead us to rationalize the wide spectrum of physiological functions that are provided by proteins. I put a few examples here. Proteins can have protective function. The skin and our hair is mostly protein. It can catalyze with enzymes which digest our food. The enzymes can be regulated by other proteins, the hormones, and an important function in our body is the transport of materials. For example, oxygen from the air is transported to our brain, to the muscles, and that is, of course, one of the essential elements of us being alive and functional. Now, just to hit home, what I want to say is the following. Enzymes, hormones, and hemoglobin can only function because they are soluble in water. If hair and skin were also soluble in water, we wouldn't survive the next thunderstorm. And both groups of proteins are built up from the same 20 amino acids, and the variations in the linear arrangement are only limited. To understand why proteins can perform this wide spectrum of physiological functions, we need to know the three-dimensional structure. Here is an example. We not only need to know the static three-dimensional architecture, we also need to learn about dynamics within the molecules and dynamics when these molecules interact with other large or small molecules. I can present the three-dimensional structures either by a surface view, or I can look through the molecule and show all the atoms. Both is important. The stability of proteins is mainly due to interactions among amino acids in the interior. The functionalities of proteins are mostly due to surface properties, because it is clear that interactions with other molecules and therefore reactions promoted by proteins will be through areas of the surface. Now, to study proteins with NMR, we need quite sophisticated instrumentation. I'm standing here in front of a 900 megahertz magnet that we use to study proteins. This is the highest field that is widely used. Work is in progress to go to higher fields, up to, at this moment, 1,200 megahertz or 1.2 gigahertz. Now, 900 megahertz is about 500,000 times the strength of the Earth's magnetic field, which we use when we use a compass, for example, to orient ourselves. In addition to the magnet, we need computers, we need radio frequency technology, and we need theory. Here is a typical description of a simple NMR experiment by the time evolution of single transition basis operators. So basically, NMR can be explained either in quantum mechanics, as we have it here, or in classical mechanics. Now, this is high-tech stuff. And you can ask, why did I get into this at all? And I've tried to give you an idea of why this happened. I mean, I'm the first member of the family who ever went to a university. My family were farmers, and I grew up on this farm in Switzerland near Bern. It's only 20 kilometers away from the stadium where Hungary lost the final in the football cup in 1954. And it's only 20 kilometers away from the office where Einstein produced his most important work from 1904 to 1907. To this farm belongs forest, which I still entertain myself. Of course, you will not see any pictures from when I was a boy, because nobody was interested in me when I was a boy. So we had to reenact things later on, I mean, 18 years ago or so. And there was a trout river that was part of the farm. That means when I was a boy of about between 12 and 16 years, I was in charge of that trout river. That means we would catch trout with an electric device. We would get the eggs out. We would grow small fish, and we would then put the fish back, so on. So I learned an awful lot about fish. And one thing that I learned, and that was extremely important with regard to my career, is that you have to catch big fish when you want to attract attention. And it is not more difficult to catch big fish than to catch small fish. And it is much more fun, and it is much more relevant. And so when I went into science, I tried to single out some big fish that were worthwhile the effort that it needs, in any case, to succeed in science. I show you one of these big fish applications of NMR, which is at least as big as this fish that's in front of me. That was actually, I caught this in New Zealand, and it's always a bit competitive. You can see here on the blackboard, I mean, I caught this fish with a line that is, the fish is, I don't know, 60 or 80 kilograms. So the line with which I caught it was 24 kilograms test. So it is really sports fishing. And actually carried off I was in first place of the fishing competition. You see, there are more fish. I caught 8 tuna in an afternoon on that occasion. Okay, that big fish in the application of NMR was prion proteins. Now, prion proteins became widely known in the mid-1990s because of the mad cow crisis. What happened was that cows became sick with prion disease. It was called bovine BSE. And it was it was really a huge catastrophe. And it was widely publicized, of course. The damage done went into the billions of euro. In England alone, a couple of 100,000 cows had to be destroyed. That means killed and burned. It swept over to Europe, fortunately only in smaller numbers, a few hundred cases in total. And everybody was scared that this epidemic among cattle would be transmitted to humans. And there were predictions in Nature, theoretical predictions, that we would have to count with 10 million people being affected by prion disease that was transmitted from the infected bovines because people had been eating meat and inner organs from infected beef for many years without knowing about it. Otherwise, the corresponding disease in humans is Creutzfeldt-Jakob disease, and it affects about 1 person in 1 million of the population. That means in Switzerland we would have about 7 to 10 cases per year. And so the prediction was that this would explode because of the mad cow disease. See, what mad cow disease does is that we like our cows, see? So this cow goes into vacation for the summer. It goes into the Alps, and they eat grass in high altitude, and that makes a famous Swiss cheese. And then they get BSc and become miserable creatures. Of course, the cow did not change from this color to the black color. This is also not a Swiss cow, it is an English cow. And so within a few months, we solved the structure of the protein that's responsible for the onset of mad cow disease. And that's how this protein looked. And it's also a new concept. It's the first time that a long unfolded protein was characterized. See, half of the protein is folded, that's the green and blue part, and about 110 residues, so that's by all accounts a very long polypeptide chain, is flexibly disordered. And here we have superimposed the 20 snapshots taken at intervals of 20 picoseconds, that is 2 times 10 to the minus 11 seconds. And you can see that the white part, what we usually refer to it as tail, moves all over the place in 1 nanosecond, whereas the folded part stayed still. Now this, on the day when this was published in Nature, we had 350 newspapers around the world reporting on this on the front page. In all, I have about that much paper accumulated, just newspaper pages, which report about the results that we obtained. 6 years later, there was no mad cow disease anymore. That's not us alone who did this. It was one small contribution from maybe a total of 20 labs worldwide who provided politicians with the necessary information that was needed to fight mad cow disease, and it succeeded. There is no mad cow disease today. That's really a very encouraging result of natural science research. I mean, what we did with the structures was that the structure would go to the parliament in Bern, I mean, that's now on the Swiss level, and we would solve, this is a bovine structure, we would solve the structure of the human protein, of chicken, on pigs, and they all look the same. And then the politicians got scared, and they did very strict measures, which did then actually, I mean, it was a matter of prohibiting certain feeds to domestic animals, and that within 6 years then did the job. So see, this is a big fish. That is worthwhile to work day and night for a while and get things done. Gouvache pour le Prion, they were actually quite right with their prediction, although we hadn't thought that it would go that far. Now, I come to another point that is important. You cannot just go for big fish. You also have to place whatever you do in perspective with the world around you and the world far away from you. Now, in the case of mad cow disease, that it was clear. Television was full of it, newspapers were full of it, so we didn't have to search, it was thrown at us. And it was clear that it would be extremely important to work on this. It is much more difficult generally in science to put oneself into proper perspective. And the only way, I think, is to read and read and read. And I'm told that even as a boy, when I was 15, 16, I would read thousands of pages of anything that came into my hands. I would also prepare exams when I was at the university by reading heavy books and never take notes, just read. And for some reason, I can recall whatever I read. And so I spent, I mean, even today, I spent already 3 hours reading articles on the internet, and I also have copies with me of papers that were collected for me by my associates, and so on. Now here, I try to tell you how I was positioned in my work worldwide when I started. In 1962, I started with my PhD work, and at this moment, I was almost 100% into sports. And also in 1962, the Nobel Prize was given for the DNA double helix. You see here, you recognize Crick and Watson. And it was given to Perutz and Kendrew for the first protein crystal structure determinations. And then, now, hemoglobin, that was the protein for which Perutz and Kendrew got their Nobel Prize. And I was interested in hemoglobin because, as I said, I was in sports. Now, this can also have direct benefits. You see, this photograph of myself training high jumping was published in Nature in 2015. Here is the reference. So that's an easy and pleasant way to get the paper in Nature. Otherwise, you may have to work hard to get there. So train a lot. Now, because of my sports, I was extremely interested in hemoglobin. It was not for high jumping, but it was for middle distance running. I was running 800 meters and 1,500 meters, and it was obvious that my performance was limited by the oxygen uptake. And so I was extremely interested in oxygen uptake. And the structure of hemoglobin at the time when Perutz and Kendrew got their Nobel Prize looked like this. You couldn't see an atom in there. You could only see rough outlines of the structure, These are laminated wood platelets that were cut out and pasted on top of each other. And you could see where the oxygen binding sites are. Here, there are two more in the back. And you can see here, this would be a helical secondary structure, for example. That was it. And so Perutz could not say anything about what happens near to the oxygen binding site. He only found out that the white and the black parts of the molecule moved against each other when the molecule took up oxygen. That's what happens in the lungs. And when it gives up the oxygen, and that happens then in the muscles or in the brain. At that point, I thought this was not enough. I took my own hemoglobin. Here, see, it's published as hemoglobin KW and PNAS, and I immediately found out that there were movements next to the oxygen binding site. You see, these are very unusual peaks. I mean, you have here one-dimensional NMR spectrum. Usually you only find lines in this range. I don't want to go into details. But now in my hemoglobin, there were lines here, which went all the way here and also all the way here. That was extremely unexpected. And that's when I became a scientist. I actually never ran middle distances faster because of this, but that was the turning point. Because within about a year, this work on the hemoglobin was very highly accepted. I mean, it was like a jump of 15 years in my career. I was reasonably worldwide known after 1 year of making these observations on my hemoglobin. You see, it was almost entirely motivated by my interest in sports and by my own experience in sports. It held up. I mean, you see, today there is a lot of doping in professional sports. I mean, early on, even at my time, we would go and train at high altitude before competition and then compete at sea level or thereabouts. And then started cheating. Athletes would go and train at high altitude, out of season, take blood out, freeze the blood. That was high in hemoglobin. And then would do so-called self-doping with their own blood. That was enriched in hemoglobin. That's why they had 3 days at the Tour de France. Every 7 days was a free day, and then they would go and get half a liter of the hemoglobin-enriched blood. That was standard from about 1970 to 1990. And then came EPO. And EPO was used to boost hemoglobin concentration in the blood. And then came Sera, which made it impossible to detect EPO, and so on. And so I stayed involved in this until I left the anti-doping Swiss about 5 years ago, because I didn't believe in the functioning of this technique anymore. But anyway, instead of looking like this, hemoglobin then looked like this. And it was clear that things happened immediately in the surroundings of the oxygen binding site. And about 8 years later, crystallography then had sufficiently high resolution to see this as well. Now, I go away now from molecules and for a few minutes talk about the use of NMR on studies microscopic objects, namely human bodies. And I put this here in my talk because it is again very strongly motivated by my sports activities. See, I don't know, this is Peter Mansfield, one of the two scientists who shared the Nobel Prize in Medicine for having introduced magnetic resonance imaging. And here is a magnet, and here is a coil that is used to put the head in, and then the patient is put into the magnet. Who has had an MRI taken here? Anyone? It's very unpleasant, a lot of noise. Well, I played football also on the side, and I played football quite long, for many years. You see here, this is just 3 years ago, in 2015. And while I was playing football for, well, it was something like over 60 years. I, of course, had some injuries over time. And so I had to check my knees. And you see, now these are pictures of my knees. And fortunately, I never had to have an operation on my knees. I mean, I had elongated tendons, but it was never so bad that surgery was needed. And so I could still play 2 years or 3 years ago. But it's important that you have the possibility of checking that you are still okay. Now, on a Monday, after each weekend during the season, the reports on the MRI pictures taken from players in the Bundesliga and probably also here in Hungary, any case also in Switzerland, attract more interest than the results of the games. Because typically 3 players per team have to go to the MRI after the game to make sure that there is no serious injury either to a knee or to an ankle. And then you learn something more from playing team sports. You see, this picture is from couple of years ago. It is actually from a FIFA exhibition game. Most of the guys here have played in the Swiss national team at some time. So that's also interesting. You get the invitations to play such games either because you can play football or because you have a Nobel Prize. Either one helps. So, but I have always liked to play with very good players, and so this has always been fun. And then, of course, when you are on a team, you learn very much with regards to running a laboratory in science. See, during the time up to the Nobel Prize, I had 249 collaborators. Graduate students, and mostly graduate students and postdocs, but also technical personnel. This includes mathematicians, theoretical physicists, experimental physicists, chemists, microbiologists, and biochemists. On average per year, that makes about 20, a group of 20. That corresponds pretty much to the size of a football team with replacements. Now, when you want to be successful, then each one of these people has to be happy while they are in the lab. Just as football players need to be happy if they are to perform well. Just to put it bluntly, if you don't have a tall center forward, there is no point to send players along the wing and hit high balls to the center, because there will be no chance to score. So you have to change the system. And so in my case, that meant if at some point I didn't have talented theoretical physicists, I just stopped doing the theoretical part and pushed other parts, but never forced anyone to do something which would not correspond to his strengths. So it's important, that keeps people happy and makes the enterprise successful. Good. Now I'm going back to molecules. And here the important word is in solution. See, we get three-dimensional protein structures, we see individual atoms, and we use nuclear magnetic resonance in solution. Now, when we proposed to do this, we were just laughed out of the room for a very simple reason. Molecules in solution are under the regime of Brownian motion. Now here, it's again very important to know what has been done in the past, because it may tell you what you can now do at your time. And so there was a Mr. Brown in England. You can see him here, Robert Brown, who was a biologist. And he worked with flowers. And flowers contain pollen. And now he lost some pollen into a water glass. Oh, because he was curious, he looked at the pollen in the water under the microscope. And of course he expected that the pollen would simply swim quietly in the water. But to his surprise, he discovered that they moved around. A small piece of pollen would move like this. It would change the direction at higher frequency than a larger piece of pollen, which would also move, but it would change direction at a slower pace. And this, he didn't understand. He published this in 1827, so almost 200 years ago. And then Einstein understood what Brown had seen, and he was able to explain what happens. It's statistical mechanics. You are at high temperature. The solvent molecules are highly agitated at the high temperature. You see, 35 degrees is a very high temperature for a physicist. It's 310 degrees or thereabouts. It is very far from absolute zero. And so this resulted in the Stokes-Einstein relation, which essentially just says, when applied to NMR, that small particles give sharp lines and large particles give broad lines. So now we understand why we can take sharp pictures of the brain, because the brain contains a lot of water, and whenever we record a magnetic resonance image, we only see the water. Nobody has ever seen anything else in a medical application of MRI than water in our body, because the water molecules are the only parts that move rapidly, whereas fat and bone and meat doesn't move, and there is hardly any background. Now, when you understand what's going on, then you have it in hand to improve the quality of the pictures. And this is still ongoing. But those who have been in an MRI machine may recall that they got T1-weighted pictures, T2-weighted pictures, and so on. And this improvement of the image quality is ongoing now, and it is based on understanding Brownian motion that was discovered 200 years ago, and a theory that explains how one has to treat Brownian motion that was done 110 years ago. Now, with regard to using NMR or any other technique to determine a structure of a protein in solution, we have the following problem to solve. The Brownian motion occurs at very high frequency for something of the size of a protein dissolved in water. It's the frequency is in about 10 to the 10 per second or 10 to the 11 per second. And the motions are stochastic. That means they are not periodic. You have no chance, for example, when you have a perturbation by the heartbeat, that's periodic, and so you can trigger an observation so that you would get a sharp picture from the beating heart. But here you have no chance. You have to directly observe the moving target. Now, any kind of device, such as a camera, that you know from your own experience, because everybody now has a handy with a camera. If anything moves faster than about with a frequency of 10 to the third or 10 to the fourth, then you don't get a sharp picture. Therefore, here, when trying to get a structure of something that moves at the frequency of proteins dissolved in water, is about 6 orders of magnitude away from what is usually practical. So a solution had to be found. And the solution is that you have to find quantities that are invariant under translation and rotation and determine the structure. And such a quantity is the distance between two atoms. See, I have here a large number of pairs of atoms. And you see that the distance here is the same as here. And it's the same here as here. So it is invariant under translation from here to here, and it is invariant under rotation from here to here to here. So once recognizing this, it was a matter of finding out how sufficiently large number of such distances could be measured to define the structure in solution. And then, of course, you needed mathematical tools to make the transformation from the distance space to Cartesian space. I mean, the distance space would then be perhaps 10,000 dimensional, and you would have to embed this into the three-dimensional Cartesian space. Now, the solution to getting this information on the distances came with the development of multidimensional NMR. That's a big fish. That's, again, a big fish, okay? It's Nobel-worthy. And instead of recording spectra on a single frequency axis, you go to two frequency axes. So instead of having such an array with a lot of overlapping peaks, you go to a two-dimensional presentation. See, you have two frequency axes, and now each peak in here, in this particular experiment, it is nosy. We also had sexy and foxy. This is nothing dirty. I mean, sexy is spin echo correlated spectroscopy. But you have to sell, and you cannot sell spin echo correlated spectroscopy, so it had to be sexy and so on. But the key experiment is nosy, and that gives us these distances. And then we needed several years of development of algorithms, and then computer program writing until we could calculate the three-dimensional structure on the basis of distance geometry principles, and then we got the three-dimensional structure from this. And now we had it. And because the distance is invariant under the Brownian motion, it can be done, and you can see each atom separately at high resolution. This gave 2 Nobel Prizes. This is Professor Ernst. This is myself. You don't recognize me, probably. For some reason, we got 2 separate Nobel Prizes, although we worked together. We also published together several dozen papers. And so Professor Ernst got the Nobel Prize in Chemistry for inventing 2-dimensional NMR, and I got the prize for solving the problem of the distance measurements and translating distance measurements into structures. Why this was dealt with separately will only come out about 30 years from now, when the records are opened. Now let me just, for the end, show to you what happens when you get a Nobel Prize. So maybe that could give you some impetus to try at least. It's rather impressive. See, before anything happens, the members of the Royal Swedish Academy sit here on the stage. There are empty chairs for the new Nobel laureates, and here are chairs for the king's family. And then, first, this is now very unusual, first the king would come in, and after the king, the new Nobel laureates would come in. And then the king would stand until we sit down, which is the only time in the year that the protocol allows others to sit down while the king still stands. And then later on, the king gives you the medal and the diploma. And yeah, this is the king on the right. Then later on, you take pictures with the king and his wife, and then the family is happy. You see, this is also important because, of course, because of the science, they had a lot of troubles to live with. Well, I mean, I was just not there much of the time, and then family life is okay again. You see, though, this all counts. Now, you see, for Ernst, the Nobel Prize came 7 years after we had solved the first protein structure, and for me, it came 18 years afterwards. However, because I had the experience of competitive sports, I was, you see, this is now something extremely important. The most difficult thing for a student to learn is to evaluate the progress of his work. To judge rationally whether a breakthrough has been made or an advance has been made or not. 90% of all scientists fool themselves in this regard. When you have been in high jumping, you know that you either succeed or fail. And if you fail, you just have to work harder and train harder. And of course, the same for running or any measurable discipline in sports. Because I had this background, I was absolutely sure in 1984 that we had done it. And I went skiing for 18 months. I never went back to the university from November 1984 to April 1986. I did 2 complete seasons skiing, and in the summer I was working on my condition, running up the mountain 2 or 3 times a week, 1,200 meters from Wengen to the Männlichen. I mean, the place where I was is Wengen. I, of course, had an office. I wrote a book. I wrote about 40 publications in addition to the book, because you can't ski for more than a few hours a day. It then becomes tedious. And that was the view from my office in Wengen. It was, of course, inspiring, and it was extremely important to document what we had done, also in the interest of my collaborators, so that all doubts could be eliminated about whether or not it is possible to see a structure of a rapidly moving object under the regime of Brownian motion. And by now 15,000 or 18,000 structures have been solved with this technique. That's it. Thank you.
Thank you very much. And now the stage is yours. And if you have any questions, now it's a question time, either scientific or lifestyle or anything else.
Thank you. So my question is, how stressful was this project of yours, like researching and then publishing all of this knowledge?
It was not stressful for me. Because, first of all, I didn't want to make a career in science. When I first went to the United States, my wife and I had stipends to study American sports. Specifically, my wife had to study modern dance, and I was to study volleyball and basketball, which wasn't played yet in Europe at that time, and see whether baseball could possibly be used to enrich the Swiss school system in sports. And so that was the job I had to do. Then on the side, I did a lot of quantum mechanics, and quantum mechanics on the NMR principle. And, but I still mostly did sports, but the scientific part was so successful that I was hired by Bell Labs. Now, when you were hired by Bell Labs, you had it made, essentially. Does that tell you anything, Bell Labs?
Yes.
Yes. I mean, if you look up at the CVs of Nobel laureates in physics and chemistry, you find that more than 60 have been at Bell Labs at around the time when I was there. 60. And it goes all the way. I mean, there have been Nobel laureates who worked at Bell at one time, also last year, and also the year before. And so you see, and then happened this, the first thing I did at Bell Labs was this thing with the hemoglobin, because I couldn't do it before. I didn't have the instrumentation. So you see, at Bell Labs we would get everything. I mean, we didn't have to ask for money, so just give it to us, and for the asking. And so I was the only one worldwide who had this machine, so I could make this spectra of my hemoglobin. So I, of course, didn't expect it would have such an impact. I was just curious to see how my hemoglobin looked. And on the side, I was running a football league. I had rented a house which came with a football stadium, small one, a full-size football pitch. And so I was essentially playing around, except that I worked maybe 14 to 16 hours a day. That, of course, is true. I shouldn't give you the wrong impression. That I still work about these hours today when I'm in the lab. So it was, I must say, it was not, I had hardly periods when I felt under pressure.
Thank you.
But I also didn't work to get the Nobel Prize. Okay, that you shouldn't. I mean, I was just interested to see whether I could get something out of looking at my hemoglobin to run faster. It's as simple as that. I mean, and then I could always have had a job as a teacher of sports and physics in high school. That was my goal. That's what we had prepared for. I was teaching for 5 years in high school, I mean in gymnasium.
Next question.
First, I want to thank you for this speech. It was really inspirational. And my question would be if you would say something to us about the future of the field, especially because there was a news some weeks ago that Google's DeepMind solved, I think, 25 or 43 protein structures. It predicted the structures correctly for that many proteins given to it. So how you see the future of the field with AI involvement? Thank you.
Oh, specifically the field of protein structures.
Yes. Yes.
Well, the field is in a state of very rapid development these days, not because of these predictions. These, for me, are not very interesting. These are small proteins, and there are still assumptions behind these predictions. And you see, we have long been able to predict homologous protein structures. You see, as long as the sequence homology is better than 30%, we could actually predict structures routinely for a long time. But what is changing the field is the advent of cryo-electron microscopy, single molecule cryo-electron microscopy, which also garnered the Nobel Prize in Chemistry in 2017. And the big change is twofold. On the one hand, it enables to study much larger structures than by crystallography or by NMR. And the second, even more important point is that you don't need to get crystals. You see, they are now getting structures. I mean, how should I say this? I mean, we used to be very happy to get the structure of one protein, and then of the complex of 2 proteins. And now they make complexes of 10 proteins and get the structure. You see, and the size is increasing. And it happens at a very fast pace. In my own field, I'm working on GPCRs, G-protein coupled receptors, and I mean we have an important role to play with NMR in this field, but the advance due to this single molecule cryo-EM is incredible. I mean, they are now, we got complexes that we have tried to prepare for years and without success because of lack of crystals or lack of sufficiently concentrated solutions, and now they are just being done. This is a big current evolution of the field. And what you can expect from it is that more and more complex multi-molecular structures will be solved.
Thank you.
Thank you. Any other questions? Yes.
So my question is rather personal than professional. Had you stood at the beginning of your career again, what would you do differently? Is there anything you would change?
Well, you see, times have changed. I couldn't play around as a student today as I did 70 years, 60 years ago. You see, I mean, it would not be possible today that you get a PhD during participation in a full-time course in sports. Just going to the lab in the evenings and getting a PhD after 14 months. It took me 14 months to get the PhD, although I was doing sports all day at that time. You see, a typical day for us would be that we would start with 2 hours of swimming, then we would have 2 hours of gymnastics. I mean, gymnastics is the wrong word. It's women's, what is this? Is it Bodenübung? What the hell is this in English? Well, women's gymnastics, I mean, as we would teach in school. And then we would have 2 hours of actual gymnastics, Geräteturnen, and then we would end with 2 hours of track and field. That was a day. And then after that, I would go to the lab and do some experiments. And everything, even then, everything I did was new, and so I could just publish it. Nobody had, later on, they found out, I mean, there are historians who then found out I was the first. When I was 23 years old, I was the first in Switzerland who did certain things. And today, it's, you couldn't do that. I think I would have to adjust to stricter rules, and it would probably be a disaster for me.
Okay, thank you.
Okay, thank you very much. I'm very happy to have been here today. I have 2 questions. The first one has to do with when the introduction was being made. You mentioned the fact that here in Hungary, a lot of the brilliant students end up leaving and going to the US or other countries. And I'm from Ghana, and we have a similar kind of trend. So I'd like to know your thoughts on that and what can be done to address that. And then the second question that I have has to do with, I'm from Ghana, and then generally, Ghana and then other developing countries, you know, there's a gap when it comes to investments in science and technology. And so I'd like to find out if you have some suggestions on how that gap could be closed. Thank you.
Well, let me try to answer the 2 questions in one go. You now have a unique chance to study here in Szeged. And it will be extremely important for your country that at some point you go back and your country can benefit from what you have been offered to learn in a developed country. I don't mean that your country is underdeveloped, but as you said, there is a gap, and it is exactly people like you who have this chance who should help your country to close this gap.
Thank you. Any other questions? Yes.
So I'm from Romania, and lately in Romania there were a lot of virus epidemics. And my question is about the influenza virus. That they say that is a big problem because the proteins of influenza can't be crystallized. Is there a possibility to analyze with NMR your method, and if you can predict for us a better cure of this disease?
of viral diseases in general, or
influenza virus, influenza virus.
Influenza.
Yes.
Well, there was a paper in Science about 3 weeks ago, which indicates that people are on the way to developing compounds that would protect against all currently endangering strains of the virus. That you can read. It's a coincidence. It was published just, I think it's 2 or 3 weeks ago. The work comes from the lab next door to mine at Scripps, from Dr. Wilson, who works together with a company in the Netherlands. And there is promise that there will be a crucial step forward in preventing outbreaks of the flu.
Well, I have a question about how you feel about your research and the what you made possible that made the world change in a way. How do you feel about this change? And the way of thinking of people that your research made them think about.
Well, I want to give you an indirect answer. I hope that with my presentation, I have also indicated that it is very helpful if the work that you do in the laboratory using advanced techniques, complicated apparatus, has something to do with your daily life. See, I think that will continue to hold. If you can find some theme in your research that relates to other interests that you have in life, I think then that's the best starting point for success with your work.
Thank you for your answer.
Thank you. Regarding specifically the NMR technology, I would like to know whether or not this technology has been used in other fields other than structural biology, or if not, are there any ideas where this technology could be used?
Originally, when NMR was first observed, Bloch and Purcell believed that its only use would be to determine the gyromagnetic ratio of nuclei, atomic nuclei with non-zero spin, more accurately than had been possible before. That was in 1946. By 1950, the chemists had found out that there is a so-called chemical shift. That opens a possibility to use the technique as an analytical tool in chemistry. So the use in chemistry is much wider than in biology. I cannot give you numbers, I just don't know, but I would estimate that there are between 20 and 40,000 NMR spectrometers in chemistry institutes worldwide, and maybe 200 instruments that are used in structural biology, just to give you a relation. That applies to inorganic to organic chemistry. And you see, during an organic chemical synthesis, you would want to get an NMR spectrum of each step. And so a group of 20 organic chemistry students will easily run 200 NMR spectra in 1 week. I mean, it's solid state NMR. I can tell you that Nestle, you know Nestle coffee, air-dried coffee. Well, Nestle has about 10 solid-state NMR machines, and they check the quality of the air-dried coffee by putting them into the NMR machine and measuring the residual water after freeze-drying. It's as simple as that. Or in Bordeaux, they check whether or not sugar has been added to the wine. There are the range of applications is very large indeed.
Okay, thank you.
Thank you. And any questions?
You told us about your experience with sport and that it helped you a lot to tell whether you worked okay enough or not. And while doing sports, you also learn to deal with hardships. And I would like to ask you if this experience helped you while doing your research, and if there were any moments when you thought about just stopping and giving up. I mean your research.
Giving up sports
or
science?
Science.
I never felt forced to. I never felt forced to do science, and if my curiosity had ended, and my love to work with young people, with students. The average age of my group in Shanghai is about 23, including the most senior people. Then I would stop. It's as simple as that. But I always enjoyed it, and I continue to enjoy doing this kind of work.
Thank you.
Thank you. So my question would be kind of a bit more personal than scientific. So as you mentioned before, you did a lot of sports, and all your work was just based on your curiosity, and you still achieved such a fame and all of that. And my question would be, is that what's your suggestion or what's your advice for today's students to even achieve something like this or the half of this?
Let me repeat. I mean, I may make it look too easy.
Yes.
I worked, well, once, you see, the important thing is to have an idea. You have to have ideas. You have to have ideas. And what I really, I mean, this I can say, I did two things. First of all, I wanted to see whether what I did is something big. And then I would also look back and see, has it been done before? And then I wouldn't do it. So there may have been extended periods of time when I just let the students work to clean up some things and was essentially blocked myself from writing, for example. And then, but I didn't go sideways and just do something to satisfy myself. I would keep the pressure up to find something important, and even if it took some time. But once I had identified something new, then I would have very long working days.
All right, thank you very much.